thanks for having me. My name is Tobias Koppers. I'm from Germany, from Bavaria, from southern Germany, and I will going to tell you something about Turbopack. So I started with web development 10 years ago when I started to found Webpack and maintained it for 10 years. So it's pretty old now. And nearly 2 years ago, I started to join Vercel and worked on with the Next.js team on Next.js and integration with Webpack and Next.js and performance stuff and stuff like that. And then, now for 10 months I'm working on Turbopack, and I'm going to tell you something about that. So first of all, what's our mission with Turbopack? So our mission is to create the successor of Webpack. So we want to align with the goals of Webpack. We want to make some kind of tool which is really like Webpack, similar to Webpack, and fulfills at least the goals of Webpack. So I know that's a really ambitious mission, and it will take years or long time to get there. But at least that's our direction we are trying to head to. So, and this basically motivates us for our project's goals. We don't want to build something that's only for Next.js. We want to build something that's framework independent. We not want to build something that's only for Vercel. We want to make something that's for the open source community, which is a community effort, something really we want to align with the goals and the motivation behind Webpack. We also want to make sure that we are building something that's as flexible and as extensible as Webpack. So we want to follow Webpack's footsteps in that kind of way. So we actually want to create a building block for the web development for the next 10 years of web development. Ambitious goals, yeah. Okay, so let's look into what's led to the creation of Turbopack and into the past, and also how it works and what's our vision with Turbopack. So all started when I was joining Vercel and worked with the Next.js team, and basically we wanted to solve some developer experience challenges, and one of these challenges was performance. So it's kind of working well, but there are some kind of problems with, or challenges with performance, especially as Next.js is mostly built on top of JS or JavaScript-based tooling, and JavaScript-based tooling for compute-heavy work has really hard time leveraging all the power of your computer, so leveraging multiple CPUs, and really JavaScript might not be the best language for compute-heavy work or for build kind of things. So basically, the Next.js team and I started to work on porting some part of Next.js or of the compiler infrastructure of web development into Rust world. So SWC was integrated into Next.js, and it's really has a lot of benefits and performance-wise. But there were also some changes in integration-wise. So there's always a boundary between JavaScript world and Rust world, and you have the serialization problems between. So there's challenges while working on that. There were also some kind of trade-offs we had to do in Next.js for performance. So one example was that we are resolving module requests in Webpack, and we had to be really optimistic about this to make it performance. Actually, once we successfully resolved something, we just assume that this is not changed, or we also assume that node modules usually don't change. And this is kind of working well for the 99% of cases, but it's kind of a trade-off, and we don't want to be forced to choose that. But there were also some implementation challenges in the Next.js team. Currently, Next.js is using 4 to 5 Webpack compilers to make all this work. One for client, one for server rendering, for edge rendering, for React server components, and a fallback compiler for error messages. And all this kind of lighter orchestration work between these compilers is not that easy. It kind of is working, but it's kind of a source of errors where you can make mistakes or forget something, or if the communication is not working correctly, and that's not something we want to be forced to. So there were also some challenges on Webpack side. So Webpack was built 10 years ago, and it still has the architecture of from 10 years ago, where applications were hundreds of modules, and web development scaled a lot in the last decade. And yeah, so Webpack architecture was not really built for this kind of large-scale, incremental build performance kind of things. So that is a problem, and we can't easily fix that because there's a lot of plugins that depend on the architecture of Webpack, and it's really hard to make backwards compatible changes to the architecture. We can't really change the architecture while being backwards compatible, but we also don't want to like break everyone's use cases by just changing the architecture of Webpack. So that's like not really a good opportunity to fix that. But on the other hand, we fixed a lot of things while I'm working on Next.js in Webpack to make it more performant, but we had like a limit on this kind of optimization we can do without rewriting everything. There were also some other changes like cache invalidation. In many cases, it's either too sensitive, so like you change something and it has to rebuild a larger part of the application while it's probably not affected. Like in an example, if you change a command, why do we have to rebuild like the module? It's like we could be like more granular in what we can cache. But there's also like one problem of the architecture is this kind of cache lookup cost problem. So what we do when doing an incremental build is we basically start like similar to a full build, start building it, and for every work we want to do, we first check if it's in the cache, if it's already cached, and then we can just skip doing that work. And that sounds great, but on large scale, if you look up like 10,000 modules in the cache, then you have this serious cost of looking things up in the cache. And yeah, that's kind of a problem. But yeah, we're talking about Lucas problems, like we're talking about few seconds of rebuilds. If you worked in the native world, you might like know that there are incremental build times of minutes or something. So yeah, we have a really luxurious problem in the web development world, I guess. But there was also some opportunities we could address while working on a new bundler. So at West, we have this monorepo build tool called Turbopack, and we can, when combining this with Next.js, we can learn a lot of stuff from each other. Like an example, Next.js has this cool granular caching. Like if you change one module, you will only rebuild one module and kind of some boilerplate stuff. But in the Turbopack tool world, you always have this caching granularity of like whole commands, and then Turbopack can learn from Next.js by having more granular caching, but also can learn by having more like a development-focused watch mode, where you can have this kind of incrementally watch thing experience by default. But on the other side, Next.js can learn from Turbopack. Turbopack has like this cool feature about remote caching, so it can actually share your cache with your team, and it's uploaded to the cloud or to the self-hosted solution, and then you can like share that with your team, and you don't have to rebuild what your college had built. That's cool. So we want to have that in Next.js, like sharing cache with the team and sharing cache with deployments, so we don't have to do like the whole work twice. But there are also some new opportunities we can offer. Like I've seen that many developers actually want to have more insight into the build process, like what's the size of the page of components, of like what the size of dependencies, and how does this pull request affect like the change of my application or the performance change of my application, and this kind of insights. We want to offer like more of these kind of types. Also related to build performance, like meta statistics, like why is my build slow, or how does this Webpack plugin affect my build time, or this kind of statistics. So we made this magic plan where we had this idea about like building something new, and the idea was that we have these common challenges about caching and invalidation and watch mode and incremental builds, and we wanted to like abstract that from like the bundler. So the plan was like to build some kind of core engine which solves these common problems, and then build a bundler on top of this kind of core engine, so we don't have to solve these problems all over again and like take care of cache invalidation in every kind of code we write. And then after writing this bundler, we just want to use it in Next or in other frameworks to make like get the benefits out of this kind of new idea. And that's basically what we did. And we always had this goal in mind about incremental builds should be independent of app size, which means my application can grow as large as it wants to, but my incremental build should still be constant in performance. So it should always be like the same time spent on incremental build. So basically, incremental build should only be depend on the size of the affected modules or affected change in my application, and not of the total size, which is not the case for Webpack, in example. So on top of this idea, we built a kind of layering system. What we plan to do, like we wanted to use Rust as a base layer, so as language. Most pressing reason was like we wanted to use SWC as parser. Because we don't want to rewrite a new parser and code generator and all this stuff. So we want to use that. So which is based on Rust. So it was an obvious choice to use Rust. But Rust also fits like fits good with our challenges. Like it has predictable performance. It has parallelism, which is easy to use, and shared memory stuff and stuff. It also has like it's a safe language, memory safety, which is a good point for remote stuff and security reasons kind of thing. But there are also some trade-offs by using Rust. Like Rust is usually much harder to write compared to JavaScript. And this could be a problem. It could be a developer experience problem when we want to offer the developer to write plugins. So we made the decision that we always want to provide like JavaScript and Rust as plugin interface. So we can always, so the plan is to always allow the developer to write the plugins either in JavaScript or in Rust. JavaScript might be a little bit slower, but in many cases that might not be relevant. But in the end, you can still start with writing your JavaScript plugin and port it to Rust afterwards if you figured out all the stuff and it's a performance problem. But in most cases, it will probably not be a performance problem. So, and on top of Rust, we basically built Turbo Engine, which is like this common core engine, which solves this common problems, caching, invalidation, incremental builds, and also some kind of abstracts this kind of common sources of external access, like file system, fetching, networking, stuff like that. And on top of Turbo Engine, we built Turbopack, which is just a bundler. It's basically doing all the stuff that is a bundler doing, like CSS, static assets, whatever, ECMAScript, TypeScript, WebAssembly, images, fonts. Well, there are a lot of things, actually. And then Turbopack can be used by Next.js as kind of bundler in replacement of Webpack. But it can also be used by other frameworks, like whatever. So let's zoom into like how Turbo Engine works. So Turbo Engine is all the magic about Turbo Engine is like the ability to write turbo functions, which is basically a function you annotate with some kind of annotation, and then it's made a turbo function. And turbo functions means that you opt into pair function memorization for caching. So it will automatically memorize or cache your function. So if you call it twice, it will not compute it twice. But we also do something for cache and validation. So we automatically track all dependencies of the function. So if you write this kind of turbo function and then you access some data, we automatically track that and build a large graph, which we call that task graph, out of all executions of turbo functions. So we have this large graph of tasks and dependencies between them, and can also make all this kind of cool graph work, like graph analytics on top of this kind of compute graph or task graph. And we can also, by tracking dependencies, we can also automatically schedule your work in the background or in a thread pool to make parallelism automatically. So by tracking dependencies, it mainly means once you access data from a different task or different turbo function, we can evade it at that point because we track it and make like scheduling automatically and transparent for the writer of the user of Turbo Engine. Yeah. You have an example of how a task graph looks like. It's really a simplified version. In reality, like a task graph has like about 200 tasks per module of a web application, so it's really, really granular. But it's just kind of idea what you expect from. So we have this graph where all these functions, invocations like tasks, are connected with each other with dependencies. And what we can do with this kind of graph, we can make incremental builds super cool. Because this is like an initial build. We have to execute all the functions, obviously, only once, but we have to execute them. But once you make an incremental build, you have some kind of source of change, like an example, a file watcher, which basically invalidates one of this kind of task or function. Like in this example, it invalidates the read file task. And we basically start invalidating or recomputing the graph from that kind of external source. And we can basically bubble the change through the graph by following the edges backwards and recompute only the tasks that are needed for this to accumulate this change into to update the graph to the new change. And this has a lot of benefits. Like we only have to touch like tasks that are really affected by the change, and we can also like stop bubbling the change. Like in this example, it's like shown here, where some change might not affect some output of a task. In example, you change some kind of code which doesn't affect imports, and in this case, it will not follow up after getting the module references. It will see like the references are the same, and it will stop bubbling the change through the graph, so we can stop at any point. But you also see that we can automatically run code in parallel. Like both of these tasks depend on parsing TypeScript, and we can run them just in parallel automatically. And basically, you don't have to think about these kind of common problems when writing a bundler on top of Turbo Engine. So this solves a lot of problems. Like we don't have this problem about single-threaded JavaScript because we are writing Rust and we have automatic scheduling and parallelization. It also solves the problems of cache invalidation. Like you can't misinvalidating the cache because it's automatically, you can't break it, or at least it's really hard to break. And it also solves the problem of too sensitive cache invalidation because we have this really granular function graph where we can follow changes and dependencies really granular way, and so it makes cache invalidation really granular and correct. It also solves the problem of many cache lookups because for all this graphs which are gray here, we don't have to do anything. We don't have to look it up in the cache. It's just sitting around, not being touched by the change at all. So it just not have any cost for inactive tasks, which makes basically you can have like a large application as large as you want to. Your change is only affected by the change performance only affected by the task you have to recompute, which is really minimal. So which basically gives us our goal that incremental build should be independent of application size. So on top of this kind of Turbo Engine system, we built Turbopack, which is basically a bundler, but with two major differences compared to Webpack. So it has a system of mixed environments. So in a Turbopack asset graph, you basically can mix environments. So you can mix server, and server is importing a client component, or you're importing edge function from a server component, whatever. You can mix environments in the graph, and it's just one compiler taking care of all the graphs. And this gives a lot of benefits, like we can do cross-environment optimization, like tree shaking between environments and that stuff. A lot of more opportunities to optimize your code. We also have this concept about lazy asset graphs. So this means Turbo Engine takes care of incremental builds, but what about the initial build? Do we want to build like all the tasks from the startup? Probably not. So we want to have like some kind of lazy system where we build a graph. In a bundler, we build multiple graphs, like a module graph and a chunk graph, and we build a graph in a way that they are like derived from the previous graph. So the module graph is derived from the source code, and the output graph is derived from the module graph. And in this way, we don't have to build like a function which converts one graph to another graph. We build like this derived graph, and they use like functions to get like references, which is a turbo function. And this way, you don't have to build the graphs, you just build it on demand when you access it. So basically, this means everything is lazy by default. All the complete graph is lazily built, and this means only if you do a HTTP request to the dev server, it will compute and read your files, build the module graph only for that kind of graph you are needed for serving this HTTP request, which makes it really lazy and should be also kind of streaming experience when you open a page on your dev server. So, and with this new bundler, we basically want to use it in Next. And for doing that, we try to move all the cool stuff from Next into Turbopack. So we have this kind of in the core, in the bundler, and also available for other frameworks. And Next.js, the build system is only left with like a few conventions and a few Next.js specific runtime code. And that's basically Next.js on top of Turbopack. Yeah, and what are the next steps? So the next steps for Next.js we basically did an alpha release at the Next.js conf, and it's open source, and we barely seek for feedback. It's obviously not ready for consumption or not production ready because it's missing a lot of features. So we want to reach feature parity with Next. That's our next step, and we also want to start dogfooding it for our own systems, which gives a lot of testing and direct connection with people testing it. But you can also test it. That would be really helpful. Of course, there are a lot of bug fixes to fix, like edge cases we didn't consider yet, and that stuff. And next year, we want to do a beta release to make it feature complete with Next.js and give it in public hands and let's test it. But our vision is larger. We want to have Turbo not as opt-in. We want to make it default. It probably takes years to do that, but the vision is to make it Turbo for everyone. And we also have a lot of ideas. When Turbo is the default, we can get rid of the complexity in the old system, which really limits innovation we can do. So we want to have a more advanced building block for making more innovative new ideas. And the next steps for Turbopack is basically to make a plugin system and move the Next.js support into a plugin, and then add more plugins from other frameworks. So we don't want to be Next.js specific. We really want to add plugin support and add more frameworks. And this should be something usable by everyone, by every framework, and it's not Next.js specific. But the vision is larger. So currently, a bundler doesn't give you that much of a control at runtime. So it's really hard to test production builds. You have to reconfigure the Webpack to make production build, or you have to redo a full build and just to test it if it's working, or if you have production-only bugs. We really want to make it more interactive. We want to give you control. In my vision, there's a slider in the dev server UI where you can just slide it from development to production and test production version of your page just in the dev server, and this kind of experience should be something we want to give you. And there's also more optimization opportunities. Currently, the optimization abilities in Webpack is really limited by most of the more advanced optimization have a really large performance cost. So currently, modules are the smallest unit of optimization. So what we can do instead is we can split up your modules into statements and declarations, makes this the smallest unit of optimization. This makes it really more granular tree shaking. We can split modules. We can split pre-bundled libraries into their building blocks. We can split modules into different chunks and make more optimization for the user at runtime. For Turbo Engine, the next steps are, it's already open source, but it's not really consumable as standalone. But we really want to make Turbo Engine something that also consumable without Turbopack. So it should be something you can build on top of if you want to build something cool and incrementally optimized thing. So there are some steps missing, we don't have a logo for it, and we want to stabilize. We want to stabilize the API. So we're still evolving. We can involve it by working on Turbopack. That's really great. And there's no documentation yet. But the plan is to make an alpha release, make a standalone usable, and then it can be used in other scenarios than bundling, maybe. But the vision is even larger. So currently, the task graph is limited to one user, to one process. And that's not really what we want to do it in future. So in future, it should be shared with your team, like I mentioned before. It should be one graph for your team, and they can share modules, share tasks and computation of tasks. And that basically works because you can trust your team that the computation that your college is doing also works for your case. And we can even go further. Computations still happen on local machines, but we can also move them, or at least some of them, to the cloud and make some kind of edge compute cloud, which computes part of your application if you don't want to wait so long for your own computer to build it. This is cool because then because you can usually trust the cloud, and if you trust the cloud, you can get something like public caching, where the cloud, when you ask the cloud to compute some node module, there's a good chance that somebody else on the world already computed this kind of node module before, so we can just use this public caching opportunity to make it even faster. But we also want to give you more visibility. So we want to have like more insights into builds. We want to have like statistics, how your build is performing, like cool summaries which says what's really affecting the current build time, and also some kind of linting or hinting system for performance where you can like describe this should not take longer than blah time or whatever. And also there's this bundle analyzer in Webpack, but it could also be like a build performance analyzer where you can have the same kind of insights which a bundle analyzer gives you, but for the build process, how long are modules taking, what is affecting your performance, this huge node module is affecting all the performance, whatever. And the vision for Turbo Repo is to get like more granular caching for everyone, like all the granular caching we have with Turbopack, with Next.js. In Turbo Repo, we could also make it for more operations, like for other frameworks, also for common file operations, and this kind of things. Thank you. That was all I have to say. And if you want to find me afterwards, I'm either in the Vessel booth, or in the Q&A room, or the performance discussion room, or in the after party. Busy day today.